So this is the second part of a tutorial sort of on the data analysis assignment. And we left off talking about a single factor with two levels, or a single factor design. But I'm going to return to the two-level situation. And we talked about this decision-making matrix for the class, and which is out of your book. And what we decided was we matched up the names, independent groups one-factor design, and the ex post facto one-factor design are independent samples, and we'll analyze them as independent samples. Whereas a matched groups one-factor design and repeated measures one-factor design are dependent samples. We're going to analyze them the same way. In other words, with independent samples, we can do a t-test or rank sum t. With dependent samples, we can do a t-test for dependent samples, or Wilcoxon-signed ranks test. Now, this choice between parametric and non-parametric alternatives is up to you based on the assumptions and how you feel about them. Okay, so let's go through an example, and I'll try to illustrate how we make these decisions. So, an elementary school teacher is offered two reading programs to use with his first graders, Direct Stars and Awesomely Whole. He would like to use the one that works best, but both authors claim that they are better than the other. The programs both claim that they're the best, okay? Before adopting one, he conducts an experiment. In one of his classes, he randomly selects 12 students to work on Direct Star, while 12 other students work on Awesomely Whole. After 6 weeks of instruction, he gives all the students a standardized reading test, a total of 300 points. So, what did this teacher find? How would you report this, or how would he report this? And more importantly, probably, is what curriculum should he select? Okay, so we have to answer some important questions about this design. And all the information, I believe, here are the data, here are the scores following 6 weeks of instruction on the 12 kids that participated in the Direct Star and the 12 kids that participated in Awesomely Whole. Okay, so what if we had a Kahoot, huh? Well, this isn't a real Kahoot. I'm just trying to liven things up here a little bit. What is the independent variable in this experiment? What is it? Is it drug amount, reading test score, teacher bias, teaching method? Well, if you said reading test score, you'd be wrong. If you said teacher bias, you'd be wrong. It's the drug amount. No, it's wrong. No, the correct answer is teaching method. He is interested in the effectiveness of a teaching method. So the independent variable in this experiment is the method, the teaching method. Okay? What's another name for the independent variable? Non-dependent variable, factor, experimental bias. It's another name for an independent variable, IV. There is no other, no, there's another name for it. No, dependent variable is different than an independent variable. It's definitely not experimental. Factor. Factor is another name for independent variable. So when we say we have a single factor design, we're talking about one independent variable. So how many factors are there? It's a little tricky. Are there one factor? Is there 12 factors? Is there 2 factors, or it cannot be determined? Ooh, that's always an intriguing option. It cannot be determined. There's one factor in this design. That factor is method. Now, how many levels of the one factor or single factor? Well, there are 2 levels of a single factor. There are 2 levels to the method's factor. Okay? All right. So, without spending a lot of time and animating and all this stuff, let's read this again. An elementary school teacher is offered 2 reading curriculums, blah, 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 blah. Is this a between group or within subject design? Is this a manipulated or subject independent variable? Is there random assignment or is there matching? Okay, so the first question is, between groups or within subjects? Are there two separate groups? Or do all the subjects receive all levels of the independent variable? Well, 12 students receive direct star, 12 students receive awesomely whole. So they don't receive all levels of the independent variable. This is a between groups design. Okay, is this a manipulated or subject IV? In other words, is the independent variable manipulated by, controlled by the teacher, or is the independent variable provided by some feature of the subject? Well, we know nothing about the subjects. The subjects are just 12 kids. The teacher controls who gets direct star and who gets awesomely whole. So this is a manipulated IV, and they are randomly assigned. He randomly selects 12 students, so he controls who gets what. All right? So this is a single factor with two levels. It's a between groups design in a manipulated independent variable. In other words, it's this first option. In other words, we get to select either doing a t-test for independent samples or a rank sum t. Now, why would I choose one over the other? Well, the assumptions of a t-test are that you have normally distributed data, that it's at the interval or ratio level, that you have homogeneity of variance, and that you have some features of random selection or assignment. The rank sum t only assumes that you have random selection or assignment. So if you feel comfortable with these assumptions, you can do a t-test. If you don't feel comfortable with these assumptions, then you maybe should do a rank sum t. So how is it that we should do this? Well, from my own point of view, and again, I'm maybe a little more experienced in statistical analysis than you are, I feel comfortable doing a t-test. I think the data are probably, the populations are probably normally distributed. They probably have the same levels of homogeneity variance, and the reading test scores are probably of interval or ratio level measurement. I feel comfortable making those assumptions. It's not anything crazy. So I'm going to do a t-test for independent samples. So how would I do this? Well, I need to do it in some sort of program, I think, that might help me do statistical analysis. In my book, that's Excel. So what I'm going to do is I'm going to open up Excel. I have an empty workbook here, and I'm going to copy in the data. Now, anytime that you can copy data is better than hand typing it in, because you are likely to make errors. So I am just going to paste this as text in there. I think it'll paste. No, it didn't paste very well, so I'm going to paste it again. That's what I thought. I would get these very crazy wide. So I'm going to change the font level here a little bit to like 10. So I know what I'm dealing with. I'll zoom it in a little bit, or out, so that you can see it. Now, I have my data. I have my direct star scores. I have my awesomely whole scores. Now, I have to do a t-test for independent samples. Well, I can do it 1,000 different ways in Excel. My preferred way is to use the data analysis toolpack, which is an add-in. And you might have learned SPSS, you might have learned whatever. I mean, you should have had stats. This is a review. I like the data analysis toolpack because it provides these features for Excel. What I'm going to do is I'm going to do a t-test. I've decided, but I have a t-test, t-test, t-test. I have a paired two-sample for means, two-sample assuming equal variances, two-sample assuming unequal variances. Which one do I do? Well, if we go back, we remember, right, that we are going to do, it's not paired. And I'm assuming homogeneity of variance. So I'm assuming equal variances and unpaired scores. So what I'm going to choose is I'm going to choose t-test 2-sample assuming equal variances. If I click OK, it asks me for a few things. Variable 1 range. Well, my variable 1 range is right here. Now notice that I've selected the name of the condition. I'm going to do my variable 2 here. Hypothesized mean difference. If there's the null hypothesis will specify that there is 0 difference. Now, since I selected A1 and B1 with labels, I'm going to click on the labels. I'm going to make my output range. I'm going to put it, let's put it right there in D1. And if I click OK, I wind up with this. Okay, let me shrink this a little bit. T-test. Now look at this nice output that I get. I get the mean, the variance, the observations, the pooled variance, degrees of freedom, a t-stat, and a p-value, a t-critical, a p-value, a t-critical. Okay, so those are my results. Now what? Well, what we probably are going to look at is one of these two p-values. Now, if I have a one-tailed test, a directional hypothesis, I would use this. If I have a non-directional hypothesis, I would use that. In either case, neither of these are significant. Neither of them are less than 0.05, right? So it's not significant. So in my results section, what I might say in this experiment is that we failed to find any differences. The teacher failed to find any differences between the two teaching methods. Now, usually what we do is we report t-test. We'll report our t-statistic with the degrees of freedom. Let's go back and look. And what do we get? We got a t-stat of 1.14, 1.141. Our p-value was equal to 0.26, which is a non-significant result. Teacher failed to find any differences between the two teaching methods. He can make a choice either way. It doesn't really matter. Okay, last thing that we probably want to do is we probably want to, or I asked you to, graph these results. So what might a graph of these results look like? Well, a lot of you did something like this, where you selected all the data and you graphed it. Now, this is a perfectly fine graph, and it is totally legitimate graph for what this is, but a graph is a very powerful means of representing your results. You should be able to look at a graph and get a lot out of it. I look at this graph and get nothing out of it. I get blue and orange, which are the colors of my beloved Syracuse Orangemen, but regardless, this doesn't summarize our results. This doesn't help us show them. It doesn't. What can you tell from this? That what's this one? Blue's a little higher than orange, and blue's a lot higher than orange, and blue's a little bit higher. Oh, but orange and blue. I mean, what do you conclude from this figure? This figure tells you bupkis, nothing. I mean, it's a pointless graph. It's filling up the space. And even if you were to make it a line graph, oh yeah, that'll make it better. What does this mean? This means nothing. There's no continuity between these points. Why is this point connected to this point? 170 is connected to 192 in what way? Those are just two kids that went on that were taught using DirectStar. So this graphs like this are totally useless. You don't want to report individual level data in a design like this. We need something else. Okay. Now, if we look in our book, or if we look at the literature, what we'll see is usually what we see is people report group means. So if I were to graph, for example, the two means, this might be a little bit more meaningful. Now it looks like here, the group average of direct stars is higher than awesomely whole, but you can see that this starts at 110. This is a little bit illegitimate because we should probably start at 0. And if we look at this figure, we say, yeah, it's a little bit higher, but we've concluded that this group is not higher than that group, that they find no statistical difference between this. Why not? Well, it's possible that the variability in the groups, was such that it made the overlap too much to be not significant, and that's the case in this example. So often what we do in graphs like this, I'm going to shrink it down a little bit and put it over to the side, is that we often show measures of variability. Now what we have here is we have the variance of the first group, the variance of the second group, but that's variance. What we'd really like is we would like the standard deviation. That's one way of showing variability of a group, is to calculate the standard deviation. Now the standard deviation is pretty easy to calculate because it's just the square root of the variance. So I use square root here. I'm going to just slide it over there. And now what we can do is we could actually add a chart element called an error bar. Now, we could do the standard error, which isn't a bad idea to do in this case. And that gives us these little whiskers, and these little whiskers tell us about the variability. We can also customize those to be a custom value. We can select these. Where we want to go. We want to go standard deviation above and below. And what we wind up with is something like this, a figure that's something like that. So this is the group mean, and this is one standard deviation above, and this is one standard deviation below. This is the group mean, this is one standard deviation above, this is one standard deviation below. That is a decent figure describing the results of this particular experiment. There were no statistical differences between these two groups, and I could even, put in my graph. We'll put it in my graph, yeah, that shows that. Those are the kinds of results that I was looking for when talking about these data analysis assignments. Okay, I'm going to go through a second example that's a little more complicated, and we'll move on to that in the next video.